Welcome everyone for this semester, for this course of smooth ergodic theory. Today is our first lecture. What I will do, I will just give a presentation of the course, and maybe probably start chapter 1, but I will focus on presenting the course and tell you briefly what we will do during this whole semester with this. And also I will tell you like what you need, the reference, and so on. So the course is smooth ergodic theory. So today is our first lecture. So I like to. So first of all, the main reference that I will be using is the book of Marcelo and Crelo Oliveira, which is Foundation of Ergodic Theory. This is by Marcelo Viana and Crelo Oliveira. Yeah, so the course is going to be as follows. So we will be meeting here like twice a week, like Monday and Wednesdays, and on Friday there will be a problem session. Okay. So on Fridays I might not be there. You might be with the assistant to solve the problem that I give during the lecture. So about every 2 weeks I might give a set of problems that you need to solve. Okay. Yeah, and also the prerequisites you need for this course. You need to know about measure theory, quite a lot. By this I mean you need to know what is Borel sigma algebra, You need to know about measures, like Borel measures. You will also need to know a few about LP spaces, like integrable functions and stuff. And also you might need quite a bit of functional analysis. Like from this, we might not need a lot. This is very big subject, so like Banach spaces. And you would also need some theorems like contraction mapping theorems, like this theorem that gives you some fixed point under some conditions, like fixed point theorems and stuff. So we might also need a little bit of like theory of manifolds, like analysis on manifolds, a little bit, not too much. Yeah, from this you might need to know what is a smooth manifold, what is a diffeomorphism on the manifold, like the tangent space, the tangent maps, and this stuff, okay? Yeah, so also I might, for the evaluation of this course, the evaluation, how it's going to be graded, is we will have two options. You can either have a completely written exam or a presentation with the oral part, with the oral exam. Because, if you want to study really dynamical system, this is a central, this is very classical subject to know about dynamical systems. So I was thinking that it's not so good to just have a presentation as an exam. You also need to know like the classical theorems that exist in these subjects. Okay, so for the evaluation we will have two parts. One part will be, you have to choose. That's what I mean. You can choose either to have a written exam at the end of the course or a presentation that is followed by an oral exam. So the oral exam is that I'm just asking you about some topics, some theorems about on this course. So that's how the exam will be. Okay. So let me maybe start with what I call chapter 0, which is like an introduction and overview. Introduction and overview. So don't be too much, terrified if you see something or if you hear something that you don't understand in this introduction, because it is an overview. It's not yet a lecture. So I might tell you the main part that we will do in this course. So first of all, this is about assume with ergodic theory, which is a part of dynamical system. So it's good to ask what is a dynamical system. So this is a dynamical system. Yeah, so to define a dynamical system, what you need like a phase space or like a base space that you have in a transformation only space. So usually we have here M is called a phase space. Yeah, you have here a phase space, or some people in other field they might call it a space of states. The different states, that space of states that you can be, and you might have. So usually for this space, for this course, we need at least this to be a topological space. A topological space. Think of R, think of the interval, think of general manifolds also, like this circle, like the torus, spheres, Rn and stuff. So we might need this to have topology, so topological space. So, as you know, when you have a topology, you can also define, Borel sigma algebra, and also you have like Borel measures. The definition of Borel measures that I will not recall here. I'm supposing that we all know what it means. And we have F is a transformation. And we have, when you have these two, this collection defines a discrete time dynamical system. Defines a discrete time dynamical system. Yeah, I call discrete here because here we have just a map that we will study iterations of this map. So so you can see this as like a discrete time dynamical system. So given a continuous, so this is a discrete time dynamical system, a continuous time dynamical system is given by a family of transformations So you have Ft, which is from M to M, where here T is in R. Okay, we will see examples in a bit. And so this is the definition, like this is a general definition of the dynamical system you can have. Now, what are we interested in here in this course, basically? So we want to study, our goal is to study the orbit of a dynamical system. So what is the orbit of a dynamical system? So the orbit, if F is invertible, So if F is a bijection, the orbit of a point P in M is given by OP, which is a set of FNP for P in M. For N in Z. So when the map is not invertible, we just consider the forward orbit, because the backward orbit might not be well defined. Like the pre-image can be a set, so you might not see what you are interested in. So in the case of continuous, also think of the orbit is Ft, where T is in Z. Okay, so this is not like a very, I would say, complete definition, because when we say continuous time dynamical system, there are some property that this family should satisfy that I will say later. Okay, so this should have the same group property. I will say that later. So an example, the first example, you can consider M to be the interval, and then F of X to be the half of X. This is an example of a dynamical system which has a property, so example 1 here. So there is this fact, I mean, you can see that for every X in 0, 1, we have F and X is converging to 0. Okay, any point if you iterate it, because if you take here F squared of X equals a half, or Fn of X in X. And you can see that this is just going to 0 because this is less than 1. So I use this example to just illustrate something that we will see later, is like to define like an invariant measure. So if you see, you can define here the Dirac delta, the so-called Dirac delta, based at 0, which is this, equals 0 if equals 1 if 0 is in E and 0 otherwise. So this is a measure. So E is a measurable set. So this is delta 0 is called is a measure. Okay. So there is something interesting here in this measure. Why I write it is that it has this property that if you take any for every phi, for every continuous function, say from 0, 1 to R, if you look at this average here, well, when you evaluate this function along the orbit of X, R equals 0, n minus 1, this guy is converging to phi of 0. And this is nothing but the integral of phi with respect to the delta measure, with respect to this measure. Okay, so this is the definition of the Dirac delta measure. Okay, so this holds for every X. So this holds for every X in the interval. So something interesting in this statement is that if you look at the left-hand side here, it depends on X. But here, this side here, doesn't depend on X at all. So this depends on X, and this does not. depend on x. And this is called like the time average. We will see this time average, like you averaging, time average. And this is just the space average because you take the integral on the whole space. So this is the space average. This is something interesting that we will see later, which holds to many dynamical systems that we will study, which is the prototype of a Birkhoff ergodic theorem. Even though for this system, you don't need to apply that theorem. So we will see what is called Birkhoff ergodic theorem. So there are many theorems, so I will just say this one. That basically, what does it say? Basically, we will see it is that time average is converging to space average. So time average converges to space average. Okay? But see that this dynamical system is not like very interesting, as everything is just concentrated at 0. That's why you see every function, wherever you start, you converge to something that just depends to the Dirac delta at 0. So this is the meaningful measure. So along this course, we will study some measures, like event measure, like measures that we call meaningful. We put some structure to say that this is a measure that sees most of the dynamics. So in this setting here, the Dirac delta is a measure that makes sense, like that sees everything that is happening for this dynamical system. Okay, so I will. This is not a very interesting example. I will write here another example, which is more interested, that we will study in full details during this course, which is an example of an expanding map. So you can consider this example. By the way, I forgot to say, for this type of system, why I said it is not very interesting or not very difficult to study, is that there is a notion of entropy that is associated to every system, like the entropy that we will see. We will study this in detail. So this is something that measures the complexity of the system. So how complex is the system? Like we have positive entropy, zero entropy. We know that like positive entropy says that you have chaotic system. Zero entropy, sometimes it's difficult to study, sometimes it's easy, like this one. So entropy, like this, is complexity of the system. So this is a quantity that measures the complexity of the system. And it is something that we will see. It is a topological invariant. Like if you have two systems that are topologically equivalent, they have the same entropy. So for this map, we can see that. So we will see that x is a half of x has zero entropy. Has zero entropy. Besides this system with zero entropy, we will study another one which is more interesting, example 2, which is always m is the interval, and then f of x is 2x mod 1. Probably some of you have seen this map. If you want to see what is this map doing, is you just draw the interval. So this is 0, 1, and this is a half. So this map, it maps 0, half to the full interval. So if you look at the graph of this map here. Yeah, and also you can see that if you look at the difference, like if you take 2 fn x minus fn y, this is 2n x minus y mod 1. So you can see that this is I mean, relatively big if you compare it to, like, if you take the ratio between this over x minus y. And we will see that these are the type of, so this is a typical, so we will see that the entropy is log 2, we will see this is log 2, which is positive, okay? And this is a typical chaotic dynamical system. Chaotic dynamical system. Yeah, also we will study like the Birkhoff ergodic theorem for this, which sounds very interesting here, which says that if you take any for every phi 0, 1 to r that is continuous, we can see that this guy 1 over n is converging to the integral of phi with respect to dx from 0 to 1. And this, as n goes to infinity, for Lebesgue almost every x in 0, 1. So this is the Birkhoff ergodic theorem that tells you that uses the fact that here Lebesgue is a meaningful measure, meaning it is an invariant measure, and also it is ergodic with respect to this measure, with respect to this dynamical system. So those are things that we will see. So the first point we will see what are invariant measures. So I just write these two systems. They are very different. This is a contracting one, and this is an expanding one. So contracting, everything is just like happening at a point. Expanding, here the orbit of the points are uniformly distributed, if you can see here. It just says that the orbit, if you look at the orbit of a point, it visits evenly, like almost everywhere along the interval. You have uniform distribution of the orbit. Whereas there, everything is just happening at a point. So in general, when you want to study systems in general, dynamical system, it's good to know whether the system is expanding, contracting, or whether it has the two behavior, like you have a contraction and an expansion. If you have a contraction, there are ways to reduce your system to something like this, expanding maps. So that's why we will study a lot of expanding maps. This is a very simple one because it is like linear and stuff, but we will study the more general case and see how to apply this to higher dimension also, like not only on the interval, like on R2, R3, or on manifolds. Okay. So if you have a question, feel free to stop me at any time. So first of all, we will study, one point that we will study is like invariant measures. What is invariant measure? It's just, you know, you have your dynamical system that is happening on a space M. This is your space M. And let's say you have a set E here. This is E, and you have your F that is happening here. Your dynamical system that is acting on this space here. And this set here is mapped to another place, like by the pre-image. So you can look at F minus 1. I should not do something. So this might be F minus 1 of E. So a measure is invariant if these two guys will have the same measure. So so invariant measure, so mu is F invariant if, mu of E equals mu of F minus 1E for all measurable. So I will write this in details. These are very interesting to study because, first of all, we will see that maybe next week, just next week, we will see that once you have invariant measure, it implies something interesting about the dynamics. Like there is a well-known Poincare recurrence theorem that you derive from invariant measure. Just having an invariant measure, it tells you that we will see that it tells you. So invariant measure existence of invariant measures imply Poincare, just recurrence. Recurrence, it just means that points, they keep coming back. Like, if you look at this set, if it has a positive measure with respect to an invariant measure, so the points that are in this set, they tend to come back always to this set. Okay? We will see this. Okay? And yeah, so yeah, we will see the existence, like when do they exist. So in general, you have plenty of them. Like whenever you have a fixed point of the system, fixed points means that, so whenever you have fixed point, mean that f of p equals p, then delta p is invariant. Like the Dirac delta based at p is invariant. Also, if you have a periodic point, we will do this in details, meaning that f, you have some k, says that fkp equals p. So if you take delta along the orbit of p, which is just defined by 1 over k times the sum of delta fi p for I equals 0 to k minus 1, this guy is an invariant measure. So in general, you think that you have plenty of them, plenty of invariant measures. But there are systems that do not have invariant measures as well. So, yeah. So after invariant measure, we will want more structure on this measure, which is ergodicity. So already I said invariant gives something interesting, which is recurrence. So we will also see already in the second chapter, we will see ergodic measures. So for this course, I will only use ergodicity for invariant measures. Though you will see in general in the literature, you can define ergodicity without invariant. So, but for this course, what does ergodicity mean? Ergodicity, it just means that you cannot decompose your system into two systems that has meaning in the measure theoretic sense. So let's say this is my phase space, this is M. So if you can have a decomposition of your space into two sets A and the complement of A, and F is invariant here, and F also is invariant here. Like if you take a point here, it stays here. If you take a point here, it stays here. So mu ergodic imply that one of these sets is negligible. So okay, it's just saying that your system is irreducible in a measure theoretic sense. You cannot reduce into two dynamical systems with this measure. So this implies that mu of A equals 1 or mu of A equals 0. Oh, by the way, I forgot. I will be talking about probability measures for this course. The measure of the full space is 1. Okay? So this is about irreducibility, if you want to say. Irreducibility in a major theoretic sense. So, also, we will see also like ergodic decomposition. So, we will also see ergodic decomposition. Oh, by the way, before I go to ergodic decomposition, so once you have ergodicity, because I said here invariance, it gives you, first of all, it gives you recurrence, which is something very nice to have. You can, from ergodicity, you have the application of the Birkhoff-Ergodic theorem. Birkhoff-Ergodic theorem that tells you that time average is converging to space average. So we have Birkhoff-Ergodic theorem that you can use here to know something about your system. So we will see how ergodicity is needed in proving Birkhoff-Ergodic theorem, like to have Birkhoff-Ergodic theorem, which is nice. Already invariance also, it gives a version of Birkhoff theorem. It doesn't tell you that. So already from invariance, you can see that this guy will converge. But you will see that it converges to something that's just a function that depends on x, and this function is integrable and so on, but it doesn't tell you explicitly like this is the limit. So already invariance, it gives a type of Birkhoff theorem, but here invariance gives a type of Birkhoff theorem, but ergodicity will give the Birkhoff-Ergodic theorem that tells you that time average is converging to space average. Okay, and there's another property that, oh sorry, I forgot to say, we will also see ergodic decomposition. Ergodic decomposition. Ergodic decomposition, it just tells you that whenever you have an invariant measure, so given mu, an invariant measure, so you need to find a partition. So find a partition of M. You will find a partition P, the partition, so this will be P alpha, alpha in some index set, so Fm. So this is a partition of M, and in each P alpha, the dynamics is invariant there, and in there I have mu alpha that is ergodic. So in each P alpha, there is a measure. So this measure is just the restriction of this one to this partition element. There is a measure mu alpha that is ergodic. That is ergodic. Okay. So we will see ergodic decomposition. And another point that we will see is mixing. So I'm adding more structure to the measure. I said I will be looking for invariant measure that gives some properties, and after we will be looking for ergodic measures for systems. And so, yeah. So I forgot to say already in this case of invariant measure, we will do it for many examples. Like we will see examples of continuous and discrete dynamical system, like flows, like continuous time dynamical system are in general called flows. I will give examples of flow and with their invariant measures, like the geodesic flow. But that is something, one might do as a presentation at the end of the course. But I might just explain the main part here, why the geodesic flow has an invariant measure. We will also see like this type of system, like if you have something that looks almost like this one, like it just does something like this. Not quite the same, like the invent measure for this one, the ergodic measures, and also, yeah, we'll go all the way to all more properties like mixing. This is something we will see. So mixing is also something very important in dynamical system and in chaotic system. It's a property that most chaotic systems that have is that, so if you have a dynamical system and then a measure, mu is a Borel measure, so mixing means that mu of f minus n a intersect b is converted to mu of a times mu of b. So for all a, b measurable. I like to explain this as, this property of mixing as a property of, how these systems, they tend to lose memory. They tend to forget their past. They tend to forget where they come from, like the orbit. If you just look at an orbit of a point, if you start at a point, you might not be able to recover the past of this point. Like most points are doing the same thing eventually. So this is something that express the chaoticity of the system. Like the fact that whenever you take a point, you take this guy, you pull it back, you take this, it's always converging to the product of this measure. This is something that tells you that this system, they tend to forget their past. They tend to forget the past of the orbit of points. Because from Birkhoff-Ergodic theorem, you might see that from this, you might see that most points, they are doing the same. They are doing the same thing here. Most points are doing the same, because this is true for any function and for almost every x. Okay, so most points are doing the same thing. So now how this system tend to forget the past is expressed by this quantity here, which is mixing. Okay, so there are many, theory about how fast this is. This can be exponential, like this conversion can be exponential in n, can be polynomial in n. So there is a huge theory of people studying how fast you lose memory here for this type of systems. Okay, so we will see mixing. We will prove mixing for many systems like expanding maps. We will prove that you have a meaningful measure that is mixing. And also, yeah, I talk about entropy. We will talk about entropy. So we will talk about entropy of entropy. So as I said, this is something that measures complexity of a system. So to see the entropy, what is like for me, the intuition I have about entropy is the following. So, so if you have a system that I raised it, that every point is doing almost the same, they are all converging to the same point. My intuition is telling me that this system is not complex. It has zero entropy. Okay. Also, if you have a system where every point is periodic, you can think of having just something on the torus, so T2. So think of this as T2, which is R2, Z2. So you identify these two, identify these two. So if I have like a flow, let's say a flow that is just vertical, that is just doing this. So I should write it like this. This is like a dynamical system. This is an example of a continuous time dynamical system where, everything is periodic orbit. So if you want to draw it on the torus, this is what you would have. So you would have, these are orbits. So this is a system where everything is periodic. Every orbit is periodic. So this is just the vertical flow on the torus. So I consider this system as also zero entropy. So for instance, so in this case, for me, I think of positive entropy as, looking at distinguishable orbits. Let's say I said I fix a scale like epsilon. I fix a scale epsilon, and I said I'm looking at orbits of length n. And I want to say, like, I don't zoom in, like I'm blind to something that is smaller than epsilon. Let's say my eyes, they don't see something smaller than a half, let's say. If something is smaller than a half, it's the same thing. Like I don't distinguish those two things. So if you look at distinguishable orbit at certain scale epsilon for n large, if you can find this number of orbits being exponential, then we say that the system has positive entropy. Say I fix a scale, so fix a scale epsilon positive and n also positive. So look at distinguishable orbit of length n at scale epsilon. We'll be very precise with this definition, okay? We'll be very precise for this. I'm just giving the intuition. So if I look at the number of distinguishable orbits of length n at scale epsilon, so if epsilon is small, if this number is exponential in n, so I said that my system has positive entropy. So this number being exponential, so this is not a very precise definition. We will get to the precise definition maybe in 2 months. Being exponential in n imply that positive entropy. We have positive entropy. So for this type of system, for instance, if I just look at this intuition I'm telling you, so already here, for n, if n is bigger than 1, so let's say all these orbits, they have the same length 1. So they have length 1. So if you pick n 100 and n 200, you still have the same number of orbits because the length doesn't grow here. So it's just, you don't see this like many different orbits. It doesn't grow. That's why from this system you can prove that the system has zero entropy. So this is a very particular case of it's called an integrable system. Also, in the contraction case, if the system is contracting, if n is big, I see all these orbits, they are just accumulating near zero. So I don't distinguish those guys. So they are all the same for me. So that system also we can think of having zero entropy. And this entropy that I'm describing is called the topological entropy. And for this course, we will also see the metric entropy or the major theoretic entropy. Okay. Do you normally like to take breaks? No, it's okay. Okay, so we will also talk about the metric entropy or major theoretic entropy. So what I described over there is the topological entropy, which is denoted by h mu. This is a major theoretic entropy. So this is again for people who do more like information theory. This is something that tells you that how much information you get from this measure of your system. So you have a dynamical system. You want to see how much information you get from this measure with respect to this dynamical system. Okay? This number being positive, we say that this measure sees a lot on the dynamics. This number being positive, we say that this measure sees a lot about this dynamics, and yeah, so, or this number being equal to the topological entropy. So we will be interested in when h mu f equals h top f. So this is the topological entropy that is described over there. So this is topological entropy. So we'll be interested in this, and also we will see the variational principle. This is a chapter that we will reach probably by November. I hope so. Is variational principle. The variational principle is just telling you that the topological entropy of a system is the supremum over mu. So I'm not very precise here. H mu of f. Of course, this has some condition on the space, m on the base space m, and also on the dynamics f. So this is a variational principle that we will see, is that there always exists a measure that realizes the entropy, the topological entropy. So we will see the variational principle, which is very interesting here. And we will see chapter 6, the 6th point, where we study expanding maps. We will apply all this to expanding map. So we will see expanding maps. So expanding maps is just mean that f prime f prime in the case of a one-dimensional map is bigger than lambda, bigger than 1. You will see this, like the derivative is bigger than 1. So as I said, we will do this whole theory for expanding map, like find invariant measure, find the measure that is ergodic, prove mixing, and also, you know, I don't know if we might be able to talk about, this measure that realizes the topological entropy. I don't know about that, but I want to. Yeah, so these expanding maps, they are very interesting because they will help to study general maps. Like if you heard about like uniform hyperbolic maps or annals of systems, you know, in general, most study that people do, they are based on, you know, knowing what happened for the expanding map. Because as I said, we are interested in an orbit. So the orbit is, you know, if you're interested in the orbit, like the feature of a point, if the 2 points, they lie on a you have a matrix, they lie on a eigenspace which is less than 1, the modulus of the eigenvalue is less than 1, in the future these two guys, they are going to converge to the same point. You see what I mean? So I'm just saying that if you have a matrix, let's say you have A, B, C, D, let's say eigenvalues lambda 1, lambda 2 eigenvalues, where let's say lambda 1 is in 0, 1, and let's say lambda 2, just to be simple, is lambda 1 minus 1. So 1 is bigger than 1, and 1 is less than 1. So you have eigenspaces. You have two eigenspaces. One is contracting, and one is expanding. So you have these two behavior on your system. To know the feature, so if you take for this type of system, that I'm just trying to convince you why it is enough in most cases to just know expanding map, to study general maps like this one. So if I have here the eigenspace here, so if I take here, so I'm linear, so I just draw this line here. So this is eigenspace of lambda 1. So if you take a piece of this eigenspace here, let's say this is E. If you iterate it, it is going to map to something small, right? So Fn of E is going to be smaller, right? Like this. So it is invariant, it is mapped to the, but it is going to be mapped to be something smaller, arbitrarily small, right? So you can think this whole eigenspace as a point. You can see this whole eigenspace as a point if you're just interested in looking on what happened in the future, because eventually any 2 points will do the same thing in the future. Eventually any 2 points will do the same thing in the future. So it makes sense in general when you have this system to take a quotient. What you do here, you have this eigenspace. Let's say on the opposite I have the expanding eigenspace, which is like this. So this is eigenspace of lambda 2. This is the eigenspace that might create problem for the future, because if I take 2 points, though they are very close, in the future they are going to expand. So if I take something very small here, let's say A here, if I iterate it, it's going to be mapped to something large. So this can be Fn of A. So usually when you study these maps, it makes sense to collapse this whole thing as a point. You consider this eigenspace as just 1 point. You take a quotient to this. You collapse all this as 1, and your system will be just reduced to an expanding map in general. So in general, one can take the quotient. So this is not something we will do, but this is just a motivation why we study expanding map, why the contracting maps is important for us, why we study expanding map. In general, one can take a quotient map and which is expanding. So if you know something about the quotient map, you can recover something about the dynamics. So that's why this is important to study. What happened for quotient map, how to find invariant measures, ergodicity, and stuff. So everything is relying on the direction that creates problem, which is the expanding direction, on the direction that makes the system chaotic, the direction that is expanding. This is the direction that makes this orbit separates. That's the direction that makes this orbit separates. So if you look at 2 points in this direction here, if you weight n large enough, even though this was epsilon, these two will be different. So you will count them as two different guys. So this is the direction that makes problem for your study. That's why that's one main motivation to study expanding maps. Okay. So I will be following everything. I think I will have time to start chapter. Oops. Actually, there is here. So again, this is just an overview, nothing, precise as a lecture. So what we will do is that in chapter 1, we will study invariant measures, as I said. So I will be following, the book, as I said, invariant measures. Chapter 2 will be about ergodic theorems and ergodic systems. and ergodic systems. So by the way, there is something I did not say, which we will also see in this chapter. Yeah, maybe there's no time to come back, but we will see it during the chapter. And chapter 3, we will see ergodic decomposition, as I said. Position and unique ergodicity. So this is also something very important. Unique ergodicity. Basically, unique ergodicity is, if you remember, when I wrote the Birkhoff ergodic theorem, you have convergence for almost every point, but unique ergodicity is something that requires this convergence to be everywhere, not with respect to the measure, okay? Like the point that it converges, it doesn't depend on the measure. And we will see examples of. And chapter 4, we will see mixing. And then in chapter 5, yeah, we will see how to say it, equivalent systems, yeah. Equivalent systems. This is also something interesting because sometimes you want to study a dynamical system, but this dynamical system is equivalent to something that is easier to study. So you just study the other. So I will just maybe draw this picture just as an illustration. So you can have on the interval these two systems. One is something that does this. So these are linear, and another one is something that is not linear. Something like this. So depending on your interest, you can think that this one is easier to study because the branches are linear. Whereas this one, you don't know how they look. Like if you want to study periodic orbits, you want to, take measure from here, map it there, and so on. And also entropy, you want to calculate the entropy of this system. Sometimes it's easier to look at this one and see that these two are equivalent. So if this is F, this is G, so let's say this was on the interval. So these systems are equivalent. It means that F, there exists H from 0, 1 to 0, 1, which is a homeomorphism, homeo. So that, that conjugate this to F composed with H equals H composed with G. So once you have this, you can see that G is nothing but G is H minus 1 composed with F composed with H. So once you know F very well, you can recover a lot of G from F. So we will study equivalent systems and what you can get from this one. So for instance, just as an example, one can see that here you lose differentiability, whereas here it is differentiable. So you cannot hope to recover something that depends on the derivative when you're doing these equivalent systems. Like for this map, you cannot hope to get something that is differentiable. Okay? So depending on your interest, sometimes it's easier to look at this one. And yeah, we will see entropy and variational principle in chapter 6. Entropy and variational principle. Okay, we will define the entropy and the properties and also prove the variational principle, which is the topological entropy is realized as the supremum of the metric entropies. And chapter 7, which is the last chapter, I hope we will get to there. Otherwise, we might organize like presentation for this one. We will study expanding maps. This is a prototype of chaotic system. All the rich properties that people talk about chaotic system, you find them in this expanding map. So it makes sense at the end to go everything, to do everything in one measure, ergodicity, mixing, do all these entropies, calculate entropy for these expanding maps. So we will conclude this course with that. Okay, so I have about half an hour. So there's time just to start chapter 1 and give some definitions. Okay. So now we are starting the lecture, the chapter 1. So in this course or in this chapter or in this course we are given M, B, mu is a measured space. By this I mean here I have a topological space. This is a Borel sigma algebra. So this is a sigma algebra that you get from the topology. So Borel sigma algebra. And this is a probability measure. So I always care about probability measures, okay? For the space, you have many examples to think of. You can think of R. You can think of the interval. You can think of, if you want to have something compact without boundary, the circle, or higher dimensional like Tn, the torus, or in general manifolds. Okay. For the measure here, think of Lebesgue measures or something that look like Lebesgue measure on the interval. So it can be something absolutely continuous with respect to Lebesgue on those stuff. So discrete dynamical system. So the definition for this a measurable transformation f from M B mu to M B mu, because when I said about measure, it's back to a there should be given a measure here. That's why we have mu. This defines a discrete time dynamical system. So it defines the discrete dynamical system. So the least condition that we have on our dynamical system is it has to be measurable. Okay, I don't want to look at crazy systems. At least we want measurable. Okay, and then an example. We have many examples. Okay, so I have given before some example, but since this is the formal lecture, it's not an overview. I will just try to be precise. An example is that M equals S1, B is Borel, and mu is Lebesgue. So Lebesgue on S1, okay? And you can think of this map F from S1 to S1, Z squared. This is an example of a dynamical system on a circle, which is just the doubling map. Because if you look at it's just like 2x mod 1 that I draw in a that one has boundary. So if you do it on S1, it is just like this. So you can think of many examples, okay? And then a continuous, I said discrete, continuous dynamical system, continuous time. Because so usually when I just say continuous dynamical system, you might think of the regularity of the map. But here I'm really talking about the time, continuous time dynamical system. So if you have a family, so definition, a family of measurable transformations F T for T in R on M V mu defines with a property, sorry. This is what I was saying before that I did not put this. So with the property that it has two properties, that f of 0 is identity. So this is identity on M, which just doesn't leave anything. And ft plus s equals ft composed with fs for ts r. So it has this composition rule. So any family that satisfies this defines a continuous dynamical system. Defines a continuous time. So an example for this, I have here an example. Yeah. So an example for a continuous time dynamical system, you can think of M being R2. So B is the Borel and mu is Lebesgue. And you can think of this transformation F, T, and V. So take V a vector on R2 ft xv is xv plus dv. This is just a translation. By v. So this defines a continuous time dynamical system. So this map, you can also define it on T2. So in the case, so check this. So I'll ask you to check this. Check that if M is T2, if M is the two torus and the slope is rational, or slope of V and the slope of V is rational, then every orbit is periodic. So if you have a rational slope, every orbit is periodic. So yeah, you can check it. In the case when V has irrational slope, we will see during this lecture that every orbit is names. And that system satisfies like the unique ergodicity property that we will see in chapter 3. Yeah. So a remark here. So remark. So observe that this example here can be seen. So the above example can be seen as a solution of an ODE, of an ordinary differential equation, and a solution of the ODE that is just dft over dt is v. Okay. And in general, actually, sorry, another remark. So in general, continuous time dynamical system arrives naturally from solution of ODE. Naturally from solution of ODEs. So this is what I'm saying in this, is that if you have here, let's say your phase space M, if you have a vector field, like here V is a constant vector field, you can think of having a vector field, you know, at every point I have a vector. So you can see that if X is here, X, Y, I mean in that, let's say P here. So FTP is just taking, you know, the curve, the integral curve of this vector field, okay? So this is just taking, you know, the curve that is everywhere tangent to the vector field. So this point here is FTP. So in general, given a vector field, so if you have V is a vector field on M, so here I might put some small structure, not only like I might think that V, like M has some differentiable structure. So if you solve this, this defines a continuous dynamical system that is also called like a flow, okay? So we will call continuous time dynamical system flow, okay? I guess. So now we have these two definitions, like a discrete time and a continuous time dynamical system. You can see when so another remark here is that so from a continuous time dynamical system, from flow, if you're given a flow which is ft, so usually I will use this vocabulary, like continuous dynamical system, which is flow. For a flow, we can extract a discrete time dynamical system by considering just F equals, by considering F equals F1, okay, for T equals 1. So from a flow, you can consider, this is called the time one map. So time one map of the flow. So whenever you have a continuous dynamical system, whenever you have a flow, you can extract a discrete time dynamical system. How about the reverse of this statement? Like, can you always, when you have a discrete time dynamical system, can you embed it into a continuous time dynamical system? Like the reverse of this. So exercise. Answer is no, and I'll ask you to find an example for this. Find a discrete time dynamical system that cannot be embedded into a flow. Into a flow. So I'm just saying that if you give me a discrete time dynamical system, can I find a flow for which this map is coming from? Okay. So the answer is no. I'm just asking you to find a counterexample. Yeah. So probably this exercise you can think about it till next Friday to meet for the problem session, and I will also give more problems. So I said I was going to start chapter 1, and I still haven't defined what an invariant measure. And yeah, so yeah, this exercise is just telling you that the reverse of this remark is false. So this is just saying the reverse of the above remark is false. Is not always true. It's not always true. So this is what this exercise you see. Yeah, I think I will just stop here for today. And probably, next week, Monday, we will start yeah, we will define invariant measures and their properties and prove their existence and stuff. Yeah. So if you don't have questions, we stop here for today.